All right, we're going to do a couple more examples here of this section 4 stuff. I'll just kind of pick some at random. So here we go, starting it off. Let's do this one next. The integral of x squared dx all divided by square root 9 minus x squared. All right, so again, anytime you have this square root constant minus x squared or x squared minus a constant or the two of them added together, it's a trig substitution. For this one, if you want to go back and look at the first video or just kind of look through your notes, I hope you're taking notes with this stuff. Whenever the constant is in front, that means that the constant is going to be the hypotenuse. Then you set your angle up and you're going to get the substitution. If 9 is the number here, we're going to take the square root of that 3, and we're going to do the trig substitution of letting x be 3 sine theta. Remember, I like to go ahead and figure out what the inside of that square root is, that 9 minus x squared. So for us, that's going to be 9 minus 9 sine squared. Just to save some space here, if I factor a 9 out of that, I'm going to have 1 minus sine squared, and 1 minus sine squared is the same thing as cosine squared from the Pythagorean identity. The last thing that we're going to need is we are going to need to know what the differential dx is. If x is 3 sine theta, then dx is going to be the derivative of this 3 cosine theta d theta. All right, now we can plug all these substitutions into our integral. So we have x squared. If x is 3 sine theta, x squared would be 9 sine squared. dx, we just found, that's 3 cosine theta d theta. Put this in parentheses so it's separated. All divided by the square root of 9 minus x squared, where 9 minus x squared was 9 cosine squared. All right, we're going to simplify some of the stuff down. First off, we have this 3 up top here. We'll cancel out with the square root of 9, 3 on the bottom. So we are going to have a 9 kind of out in front. I'll just put it out of the integral altogether. We have a sine squared. We're going to have a cosine up top. In the bottom, I have a square root of cosine, so those two cosines cancel out. It looks like I'm just going to have sine squared d theta. Okay, this is something that we saw how to do in the last section. Remember, when you have even or odd exponents on sines and cosines, we have some techniques and some cases of solving that. Whenever you have an even exponent, that's when you want to do that substitution of either 1 plus or 1 minus cosine 2 theta all over 2. For sine squared, it is the minus 1. Leaving the 9 out in front, this is going to change into 1 minus cosine 2 theta, all divided by 2 d theta. I can pull that 2 out as a 1/2, so now I have 9 halves out in front, and then I can go ahead and find the antiderivatives. So I'm going to have this 1, that 1 is going to go to theta, minus cosine 2 theta has antiderivative 1/2 sine 2 theta. All of that plus c. All right, so we can distribute the 9 halves back in, but we're going to need to figure out what theta is in terms of x and what sine 2 theta is in terms of x. Okay, so the theta, let's go back up to our substitutions here. We have these two equations here for our substitutions. X is 3 sine theta, and then 9 minus x squared is 9 cosine squared. I can solve for the theta from this first equation. If I divide the 3 over, I get x over 3 is equal to sine, and then if I take the sine inverse, I get the theta by itself. So just kind of showing you in scratch paper what's going on here. We have x equals 3 sine theta. To solve for the theta, we're going to divide by 3, and then take the sine inverse. So this theta, we're going to substitute with this. All right, we still have this sine 2 theta, though. That, again, scratch paper stuff. Sine of 2 theta, we do not have one of our identities or our substitutions up top for. We're going to have to use the double angle identity. 2 sine theta is the same thing as 2, what did I say? Sorry. Sine of 2 theta is the same thing as 2 sine theta cosine theta. That's on that identity sheet. Sine theta we can get from this equation here. So this I'm just going to replace with x over 3. Cosine theta is going to be a little bit more work. From these equations up top here, I have 9 minus x squared is equal to 9 cosine squared. I'm going to divide the 9 and then take the square root. So I hope you can see it comes out to be the square root of 9 minus x squared, all divided by 3. All right, and then we can just simplify this down a little bit. So we have a 9 on the bottom. So we're going to have 2 ninths, and then just x times the square root 9 minus x squared. This is what we're plugging in, remember, for sine 2 theta. So just starting back here, 9 halves theta is now going to be 9 halves sine inverse of x over 3. That's going to be minus 9 fourths sine of 2 theta, which was this thing. 2 ninths x square root 9 minus x squared plus c. All right, and then just all we can really do now is just multiply those constants together. So 9 halves sine inverse x over 3. Multiplying these together, the 9's cancel, and then the 2 over 4 is going to be 1/2 x square root 9 minus x squared plus c. All right, so an even crazier looking answer, but again, if you take the derivative of this thing, I promise that it comes out to be x squared over square root 9 minus x squared. So we're doing these trig substitutions. All right, I got one more example. So let's look at this next one. I'm going to skip ahead a little bit. Here's a pretty good one. Let's look at this one. So let's do the integral from 0 to root 3 over 2, 4x squared over 1 minus x squared to the 3 halves dx. Okay, again, we have the constant out in front, which means that the substitution that we're going to use this time is going to be sine again. My a is just 1, so x we're just going to let to be 1 sine theta, which means that 1 minus x squared, which is 1 minus sine squared, is just cosine squared. And then dx, if x is sine theta, dx is going to be cosine theta d theta. All right. When I put all those substitutions back into my integral, I'm going to have 4x squared, which is going to be 4 sine squared. That divided by this 1 minus x squared to the 3 halves, that was cosine squared, so we're going to have cosine squared to the 3 halves. And then the dx, where my dx was cosine theta d theta. Okay, so again, that's plugging all of these substitutions in. 4x squared, so 4 sine squared. That 1 minus x squared was cosine squared, that's to the 3 halves. And then finally the dx was cosine theta d theta. Usually with the substitutions, I know I like to go through the end without plugging in the numbers until the very end, but we have changed variables, right? This 0 to root 3 over 2 was in terms of x. I'm going to figure out what the roots are in terms of theta, so they're going to change. I'm using this equation here. So if my x is 0, sine of 0 goes to 0, so that's going to stay 0. But if my x is 3 halves, not 3 halves, sorry, root 3 over 2, we're looking for the angle that if I plug sine into that angle gives me root 3 over 2. And that angle is something, pi over 3. So just have a unit circle in front of you, or just search or Google unit circle, and you can find that pretty easily. Okay, so we've changed the limits to now be in terms of theta, which means we're not going to have to change it back to x at the end like we have been doing. All right, so the 4, there's nothing else that'll cancel out with that 4, so I'm just going to bring that out of the integral altogether. We have the sine squared. Nothing's going to cancel out with that, so I'm just going to leave a sine squared floating around. I have cosine squared to the 3 halves. Anytime you have an exponent raised to another exponent, you multiply those two things together. So cosine squared to the 3 halves is now going to be cosine cubed here in the denominator. And then we still have this cosine theta floating around d theta. Okay, so this cosine theta is going to cancel out with one of those cosine thetas. Then I have sine squared over cosine squared. Sine squared over cosine squared is the same thing as tangent squared. I still have these limits, 0 to pi over 3. I just haven't been copying them down. All right, we looked at some of this in the last section as well. So that we're going to change using the secant. So tangent squared is the same thing as, I think it's 1 minus secant squared. No, secant squared minus 1. D theta. And then these we can just find the antiderivative for. Remember, secant squared has antiderivative tangent. 1 has antiderivative theta. And now we're going to plug in from 0 to pi over 3. We do not have to worry about changing back over to x because we've already made our limits in terms of theta. Okay, and then we just plug it in. So tangent theta, plugging in root 3 over 2 is square root 3. So that's, again, coming from the unit circle. That's going to be minus theta, so pi over 3. That minus plugging 0 in. Tangent of 0 is 0, minus 0. So this just is nothing, basically. And this is going to be our final answer. I'll go ahead and distribute the 4 in. 4 root 3 minus 4 pi over 3. Okay, great. Moving on to section 5.